Hello, welcome to Empowered Learning. This video will be about the mean value theorem, what it means, what it's trying to communicate, and seeing this particular theorem being applied in examples. The first thing we are going to talk about is to get a visual representation of what the mean value theorem is trying to communicate to us. So as you can see here, I have a function, and this is a function here, f of x. And notice that this function here is continuous everywhere in between this closed interval from x equals a here to x equals b here. Okay. The next thing that we see is that since this function is continuous on this closed interval, we know that every x value in between x equals a and in between x equals b will have a corresponding y value that goes with it, okay? And so also note that from x equals a to x equals b, if we wanted to figure out what's called the average rate of change of this particular function from x equals a to x equals b, then that would be the secant line that you see right here, okay? Now, also notice I've drawn some tangent lines here at certain points. So I've drawn one here and I've drawn one here, okay? We're going through these points, I should say. And notice that all three of these lines are parallel to one another, meaning that they share the same slope. Now, what the mean value theorem essentially is trying to figure out is it's saying if you have some function that is continuous over a closed interval of x values, then can you tell me any point or points on the graph of that function in between this interval that have the same slope of the tangent line as that matches the slope of the secant line, okay? So to put that another way, I've written out this question here, and it says, if we consider some function f of x that is continuous on a closed interval, then what point or points, and of course I've labeled them c sub I and f of c sub I, on the graph of the function f of x would have a tangent line that has the same slope as the slope of the secant line of our function, of course from x equals a to x equals b. That is essentially what the mean value theorem is trying to ask. Now, you're saying, yep, that's great, but why would that be important? Okay, I'm actually going to share an interpretation with you through example. But the first idea that comes to mind for me, which is not the example I'm going to show you, would be how we know when the low and the high temperature is for a particular area for each day is. Of course, we know that for each day, temperature, of course, starts off low in the morning, rises, gets high, about noon in the evening, then it goes back down again, okay? And of course, is this ebb and flow day after day after day. Of course, when it gets hotter, of course, the ebb and flow is kind of going like this. When temperature gets lower, the ebb and flow is going like this, okay? And so what we are, in this example here, we're considering a 24-hour period. So let's say possibly from here to, let's say, here, okay? And we know that on average, temperature change from this point to that point, which would be this line here. And so if we saw what the average change would be, one of the things we could do is look at what the slope of the tangent lines would be at this point and at this point. And we could say, all right, well, this will be, I guess these points right here would be the times and temperature in the day to where the change in temperature, of course, for the low and for the high here, would actually match the same rate of change as what we see here going from, within this 24-hour period here. So this gives us a way to be able to say, hey, at what point in the day is the temperature changing the same as the average change in the temperature over all the day. Okay. And so this is indirectly one of the ways that we could find what the high of the day is. And of course, that would be real easy to find if we had a situation like this, where let's say our temperature within this 24-hour period started and stopped at the same time. Then of course, here, slope of the tangent line would be 0 here, slope of the tangent line would be 0 here, and slope of the secant line would be 0 here. And of course, this would be our low temperature for the day, and this would be our high temperature for the day. Okay. And that's assuming here that we're looking at a period here, maybe it's 24 hours, maybe it's 28 hours, maybe it's 36 hours, where the change in temperature from the time when we started measuring to the time we stopped measuring here, that change was 0. And of course, that gives us a good idea of what the high and what the low is. However, this situation that I described down here is what happens whenever we have the high or the low for the day. And we know that over the course of days, the temperature is steady rising. Whereas if I did the same thing on this end, that would be the same type situation, but we know that the temperature is decreasing over a matter of days. So that is one example of how we could actually use the mean value theorem here. So what we're going to do next is we are going to sort of backtrack for a second, talk about this mean value theorem in terms of all the other theorems that are related to it. Some of them will be foundational theorems that the mean value theorem sort of stands on. Other theorems will be variations of a theme of this particular theorem, meaning, hey, if we single out a particular type situation from this general theorem, then we'll get what this new theorem is. All right, so we see here that because of what we talked about, the mean value theorem is essentially stating conditions of some function f of x for which the aforementioned event, which is when are we going to have points in between x equals a and x equals b that have corresponding tangent lines that have the same slope as the slope of the secant line. We basically see that if we have a continuous function over a closed interval, we can have some kind of guarantee of that happening. Okay. Now, as I mentioned before, we're going to look at some other theorems that we're sort of standing on the shoulders of so that you can see how the mean value theorem sort of relates to all these other theorems that we've been talking about. Of course, we'll start off with the intermediate value theorem. And that is a very foundational theorem. You've probably learned about it or was exposed to it in either a college algebra or pre-calculus course. Of course, we see it again in a traditional first-year calculus course as well, because of the fact that it is so foundational. And so even in your algebra courses, when you were learning Algebra 1, Algebra 2, you were actually using the extreme value theorem to do a lot of things. You just didn't know it. Okay. We're also going to talk about the extreme value theorem again. And I say again, because if you're watching the videos I've made in succession here, you notice that the video that actually comes before this one is the one on local extrema and global extrema. And so in that, we know that the extreme value theorem gives us some other conditions as far as global max and global min values being guaranteed whenever we have a continuous function on a closed interval. Okay. Now, Rolle's theorem is just going to be a very special case of the mean value theorem. Okay. And so we're going to see what that is. And actually, you've already seen it. I just didn't tell you that's what it was. But again, once we kind of go through everything, hopefully you'll see how all this fits together. And then you'll see how we actually could use this in an example. All right, so the first theorem we are going to review is the intermediate value theorem. And so the intermediate value theorem, if we state it formally, we have some function that is continuous on some closed interval of x values. Okay, if we have those conditions, then we're guaranteed to have at least one solution to this particular equation. Okay, now what f of c is equal to n actually means here is that this value c is going to be a value that is strictly inside of this interval here. So c is going to be somewhere strictly in between a and b. N is going to be a value that is strictly in between the corresponding y values that goes with these x values here. And we know that these y values are actually going to be defined because we know that the function is continuous over this closed interval, which means that every x value from x equals a to x equals b is going to have a corresponding y value to go with it. Okay. And the other condition here is that we know that f of a in general is not going to be equal to f of b. And of course, that's important so that we can avoid the constant function type situation from some point to another point. Okay. Because whenever we have that, the intermediate value theorem can't really tell what's going on per se. So we have to have some variation in between what this point a f of a is and what this point b f of b is. Okay. Now, I've said all of that, but really what the intermediate value theorem is basically saying is that if I have a function that is continuous over a closed interval of x values, where f of a and f of b are not equal to each other, then it's basically saying that, hey, I can assume or I can guarantee that if I pick any value c that's actually going to be strictly in between a and b, I am going to find a corresponding point on the graph of that function. And the point on the graph of that function is going to be in between the point a f of a, and of course the corresponding y value for that, and between b f of b. Okay. So real simple. Now I'll just do like a quick example here. If this is some function that is continuous on a closed interval here, then if this is my value c, then if my function's continuous over a closed interval, I can tell you, yes, I actually have a corresponding point in any value here. And I'm going to be able to tell you the corresponding y value for it. And that y value for it is going to be lower than the corresponding y value for this, but higher than that. Okay. It seems trivial, but is very important because it lays a foundation for a lot of things that we do in algebraic math and in calculus as well. Now, the extreme value theorem, it stands on the shoulders of the extreme value theorem. Okay. And so it does that because notice that we start off by saying let f be some continuous function on a closed interval. Okay. Now, if we know that some function f is continuous on a closed interval from x equals a to x equals b, then we already know the intermediate value theorem applies. So that means I have points that correspond to x equals c, which are strictly in between these two values. And I know that my corresponding y values are going to be in between f of a and f of b. Okay. So it says, then there exists at least one global max value and at least one global min value such that if I had two values that are in between these two endpoints of my domain here, we know that c and d are going to be inside this interval here. Then I know that, hey, if I got c and d here, then I'm guaranteed to have this and this. Okay. Now, the part where the extreme value theorem sort of veers off from the intermediate value theorem here is that we could have a situation that looks something like this with the extreme value theorem. And what I'm saying here is that we have f of a and f of b being the same value here. And of course, notice that my, I'll call this my d f of d and my c f of c values are going to be larger than, or larger or smaller than this. Okay, so it's not going to be strictly in between there. Okay, so what's actually happening here with the extreme value theorem is that we use some of the properties here. We know that we're going to have this particular solution here, but what the extreme value does, it actually extends the intermediate value theorem to where we are not bound by this particular condition here. Okay, we're not bound by that, and we're not bound by this. Okay, so as long as the values that I pick are in between, and I know that the corresponding y values to the n values of my closed interval are defined, then I can take the properties of saying, hey, I know I should have a point here in between x equals a and x equals b for any value that I pick in here. And it says that, hey, it doesn't matter whether your corresponding y values are in between f of a and f of b or not. Okay. But again, the whole property that if it's going to be continuous, then I know I have some point on the graph here. That's the part of the immediate value theorem that we carry on and let that filter into the extreme value theorem. And so we have to have both theorems. Okay. So of course, this theorem just says that, hey, well, we're guaranteed to have a point if, again, we have some value c. It's going to be in between f of a and f of b. This says, well, guess what? Even if we don't keep these two conditions here, I can still guarantee you that we're going to have some defined points on the graph. And on top of that, those defined points are going to be characterized as at least one global max and at least one global min. Okay. And so note here that the closed interval method here is actually used to find the global min and max values. And so I also covered that in the video on finding local and global extrema. And so you could look at that video to review that if need be. All right, so what Rolle's theorem is, and I'll go ahead and show you this one, is basically says here that if we have this result of having at least one solution to this particular equation if we know that our function f meets the following conditions. Okay. Now, from the local extrema video that I made, we know that f prime of some value c, where c is a number, again, that's in between a and b, if that's equal to 0, then we know that that means that, hey, I have a smooth peak or smooth dip in my graph at x equals c. Okay, so that means that at some value c, f of c, my function is either going to look like this with this point, or it's going to look like this. Okay, so that's essentially what this particular equation is. If we wanted to interpret it, that's what it would mean. Okay, now what has to happen for us to have a guaranteed situation like that? Meaning, when am I going to have a guaranteed peak, smooth peak, or smooth dip in my graph? Okay, well, first, function is continuous on a closed interval. And so notice how all these theorems have the base condition of the function has to be continuous over a closed interval. The next thing is that our function is differentiable on the open interval. So that means that the derivative exists everywhere for every x value that is strictly inside of x equals a and x equals b. Okay, we're not considering it on the n values x equals a and x equals b, but any values that are strictly in between that, we're saying the function has to be differentiable. Now that makes sense because if we go back to one of the things that we know about differentiability, we know that we cannot take the derivative of a function at the endpoint of its domain, okay? So that means if this was my function here, I would not be able to take the derivative of this function at x equals a. I wouldn't be able to take it at b. Why is that? We know because the derivative of a function is defined as the limit of the difference quotient, okay? I'm going to write that all out. And of course, for a limit to exist, this limit has to exist both to the left of 0, or left of h is equal to 0, and to the right of it, okay? And notice here, if I was to try to take the derivative of this particular function at this point, I do not have any behavior to the left of x equals a. So because of that, if I try to evaluate this particular limit here, and I could actually write it in a different way to kind of bring in the x equals a, but essentially the limit is not going to exist here, okay? So that's the reason why we can't take the derivative at these n values, okay? All right, so we know that our function will be differentiable for any values that are strictly inside of the values x equals a and x equals b. But then the last one, which is the important one here, which kind of brings everything together, is that in this case, we see that f of a and f of b are equal, okay? So essentially what we have is a situation like this, okay? Where since f of a and f of b are equal, notice that the slope of the secant line that's going through those 2 points here is 0. And if I was to pick this point and draw the tangent lines for it, the slopes of those tangent lines would also be 0, okay? And if you remember, this is exactly the situation that I had drawn when I said, hey, the temperature starts and ends within a 24-hour period at the same temperature. And here we could figure out the low and the high for the day in a particular area here. So when I actually mentioned that, what I was actually applying was Rolle's theorem, okay? And also notice that this is a variation of a theme on the actual mean value theorem, where the mean value theorem takes into account this situation, but it also takes into account this situation where the function is increasing, as well as this situation here where the function is decreasing, okay? And so, of course, the mean value theorem is sort of the catch-all for Rolle theorem when the secant line is equal to 0, as well as a variation of the thing, when is the slope of the secant line positive, when is the slope of the secant line negative. Mean value theorem takes care of all of that, okay? All right, so if we wanted to write out in formal mathematical terms, what is the mean value theorem saying? It's essentially saying that there's going to exist at least one solution to this equation here, where the left side of this equation is saying what is the derivative of our function at a particular value c, mainly that point that we're going to draw a tangent line through. So we could say, well, this is going to be slope of tangent line, okay? And the right side of this graph is just another way of saying the slope of a line in general, or the slope of a secant line, okay? And of course, we know the slope of a general line, which is slope of a secant line, will just be y2 minus y1 over x2 minus x1. Or if we were to have the points a f of a and b f of b, and let's make that look a little better here. So we had that, and then let's say we wanted to label these as x1, y1, and x2, y2, then what we would have is essentially what we see here, okay? So again, at what point c f of c, draw that again. At what point or points C, f of C, will the slope of that corresponding tangent line be the same as the slope of the secant line? Okay, and we could write this particular equation from this theorem either in this form, or we can just multiply both sides by b minus a and have it in this form. Both mean the same thing. So what we're saying here is that we are guaranteed to have a situation like this for at least one value in between, strictly in between a and b here, if our function is continuous on a closed interval, and if we can verify that our function is differentiable everywhere strictly in between x equals a and x equals b. Okay. So again, mean value theorem guarantees that you will have at least one point on the graph of your function that will have a corresponding slope of the tangent line that's going to be the same as the slope of the secant line of that function from x equals a to x equals b. Guaranteed to happen if, number one, your function is continuous on a closed interval, and two, your function is differentiable everywhere strictly in between x equals a and x equals b. Now, this note that I have here, basically all it says is that this mean value theorem here is extending the idea of Rolle's theorem, which is our situation that's kind of like this, where the slope of our secant line is 0 here. So we know we got some situations where we got some points that also have horizontal tangent lines. So it's just extending this idea for not just this situation here, but again, whenever our function is increasing like this, or if it's decreasing like that. Okay, that's essentially what all of this is trying to say here. Okay. All right. So what are the possibilities for what a graph would look like without loss of generality for the mean value theorem? Okay. So notice that I have these conditions here. Now this graph, which is f is constant, remember that the intermediate value theorem could not handle this situation here. Okay. So based upon the different ways that we interpret it, the intermediate value theorem would not be able to help us here, okay, in guaranteeing that every point that's in between x equals a and x equals b, where every x value between x equals a and x equals b would have a corresponding y value to go with it. Wouldn't be able to help us there, okay? But extending this idea to make those two conditions of f of a and f of b not being equal, throwing that away, and forcing the corresponding y value for x equals c to be in between f of a and f of b, we throw that away and employ the conditions of the mean value theorem. We can now say that, yep, I know that every point from x equals a to x equals b, well, in between x equals a and x equals b, if I have a constant function here, then the slope of this particular, the slope of the tangent lines that goes through all those points will be the same as the slope of the tangent line that goes in between a and b. And of course, all that's 0, so it makes sense. This is the situation where your function, kind of increases, then it starts decreasing. The main thing here is that the slope of the secant line is positive. This is the situation for where the slope of the secant line is negative. And this is the Rolle's theorem situation where the slope of the secant line is 0. And of course, in this case, we would have basically some point right here whose slope of the tangent line would match the slope of the secant line here. And in this case, we'll probably have something, I think, about right here, whose slope of the tangent line would match the slope of the secant line here. Okay. All right. So now we're going to talk about another real life interpretation here. And I know that I've copied this and it doesn't look so great. So what I'm going to do is draw some of this in so that you can actually see it. So here we actually have a point here, and there's a line that goes down like this. Okay. All right. And so if we had a car that was accelerating from 0, and we'll just say feet per second here, and it takes 8 seconds for it to go 352 feet, its average velocity, which would actually be, of course, average distance, well, the change in distance over the change in time, would actually be just 352 feet divided by 8 seconds, which is 44 feet per second. Okay. Now, this mean value theorem is basically guaranteeing that if our car started at let's say 0 feet and went 352 feet in 8 seconds, never stopped at all, which is sort of modeling the function as being continuous from x equals 0 to x equals 8, then it guarantees us that at some point our car was going exactly 44 feet per second, or if we want to translate that to miles per hour, it will be 30 miles per hour. So if we know that, again, if we went 352 feet in 8 seconds, and this car was continuously moving during the whole time, then the slope of the secant line going through this particular function here, from this point to this point, will give us the average rate of change, or in this case, average velocity. And we know here that there would be some point on the graph of this function that's measuring the position of the car, to where we can say, at what point was the car going the same velocity as the average velocity from 0 seconds to 8 seconds? We can guarantee that the car did that at some point in between x equals 0 and x equals 8. Okay, so that's another way we can interpret the mean value theorem. So I know another way I've seen is that if you have two runners that start a race and finish a race at the same time, then at some point both runners were running at the same speed. Okay, if they start and finish at the same time, then at some point they may still be far away from each other, but at some point they're running at the same exact speed. Okay, and we can guarantee that because of the mean value theorem. All right, so the mean value theorem is like a big theorem, and of course, normally after big theorems, we have follow-up theorems from that. The fancy word for them in mathematics is called corollaries, but really all that means is just a basic fact, or as a byproduct of this big theorem, we have these other things. Okay, and so I don't like to call them corollaries because that sounds too fancy. I just kind of want to communicate it simple. It is a basic fact after we've stated a major theorem. Okay, and in this case, this major theorem is the mean value theorem. So what is our first basic fact here? Well, it says that if we know that our function, when we take the derivative of it, is going to be 0 for every x value that's going to be in between x equals a and x equals b here. Of course, you'll be given what x equals a and x equals b is. Then we know that f is going to be a constant function for all those values in between x equals a and x equals b. Okay, so essentially you have a horizontal line, and the horizontal line is going to look something like this. And we can't really say what's going on specifically at x equals a and x equals b, but what we can say is everywhere in between it, we know we have a constant function if the derivative of this particular function is going to be 0 anywhere in between x equals a and x equals b. Now, if we come back to this situation that we had here, I'm going to erase this part here, but if we come back to this first figure here, this is essentially what that first basic fact is trying to say. Of course, since we have a horizontal line segment here, we know that the derivative of this particular function will be 0 everywhere in between x equals a to x equals b. Of course, that will be guaranteed. All right, so to build on that, our second basic fact says that if we are comparing two functions and the derivative of those two functions are equal for each x value that we're considering in this open interval, then we know that there is going to be a constant such that one function could be just written as the other function plus a constant, okay? In other words, we know that the difference in between f and g would just be some constant or a constant function, okay? An example of that, let's say if I have the function f of x is equal to 2x squared minus 1, and g of x is 2x squared plus 2, okay? If I take the derivative of these two functions here, of course, derivative of both of these is going to be 4x. So the derivative of f, derivative of g are the same. Let's say I'm considering this over all real numbers here. Then, of course, the difference in between f and g here, okay, if I say f minus g, so let's say minus, and let's say I do a minus here, then, of course, the difference in between these, if I add them, of course, that's going to cancel, and minus 1 minus 2 is going to give me a minus 3. So that's what that basic fact is trying to communicate to us. And so we'll know this without us having to even do anything. If we know that, hey, we have two functions that have the same derivative over this over this open interval of x values from x equals a to x equals b. Now the geometric translation of this basic fact just basically says mean value theorem states that graphs of functions that have identical derivatives can differ only by a vertical shift in within this x value interval here from x equals a to x equals b. And of course, if we were looking at the graph of 2x squared minus 1, in general, that would be a graph that looks something like this. Whereas the graph of, I'll rewrite this, 2x squared plus 2 would be the same thing, but it'll just go up here like this. So geometrically, the only difference in between this first function and the second one would be a vertical shift. All right, so now we are going to look at our first example of applying the mean value theorem here. And so what we want to do is verify that we have some function here, and this is going to be a cubic function. We want to verify that this function satisfies the three conditions of Rolle's theorem. And remember, Rolle's theorem is a very specific case of the mean value theorem where f of a and f of b are equal to one another, okay? So let's go back and review those three conditions that we have to have in order for Rolle's theorem to be realized before we get into this example. All right, so if you remember Rolle's theorem here, we said that there exists at least one solution to this particular equation here. And remember, we said that this just means that we're guaranteed to have at least one point whose corresponding tangent line is going to have a slope of 0 if we know that condition 1, function is continuous over a closed interval in between a to b. The function is differentiable on this open interval from a to b, and f of a is equal to f of b. So those are the three things that we need to test out. Once we test out those three and we see that our function under the given closed interval meets those conditions, then we can apply Rolle's theorem. All right, so condition number 1, our function is going to be continuous on this closed interval from 0 to 3. Now, since we know f of x is a cubic function, by definition, that's a polynomial. And one of the things that we know about a polynomial is that its domain is all real numbers. So that means that it's also continuous for all real numbers, okay? And because it's continuous for all real numbers, we know that it will be certainly continuous over this smaller interval from 0 to 3. So that one was easy. Condition number 2, we need to find out if our function is differentiable, okay? The easiest thing to do here is to say that, and I'm going to do a little bit differently than what I've written here. But if we take the derivative of our function, that's going to be 3x squared minus 2x minus 6. Okay. Let's try to make that look a little better. So this is our derivative. Notice that our derivative is also a polynomial. Because our derivative is a polynomial, it is also continuous for all real numbers. If it's continuous for all real numbers, then we know as a byproduct of it being continuous, it can also be differentiable. Okay, so we know that the converse of that is not true. We can't say, I don't want to overcomplicate it, so I'm just going to basically say here, because we have a polynomial here, it's continuous, and if it's continuous, then we can take the derivative of it at any x value, and we're going to get another real number out. And because of that, we know that this function is going to be differentiable for all real numbers. If it's differentiable for all real numbers, then it's also going to be differentiable for every value in between x equals 0 and x equals 3. Okay. And so I put here that polynomials do not contain things such as discontinuities, vertical tangent lines, sharp corners, or cusp, and it has no restrictions on its domain. And so because of that, these are some of the things that would possibly make us not be able to take the derivative of a particular function at a particular x value. But since polynomials don't have that, we know that that function is going to be differentiable over this open interval. Okay. Now, condition 3 is the easiest of the two. We just verify that f of 0 and f of 3 are equal to each other. Okay. And so we see that that's the case. Okay. So we know that from what we see here, we have a function that meets all 3 conditions of Rolle's theorem. Okay. So because of that, we know that we are guaranteed to have a solution, meaning a solution to this particular equation here. So that means if I take the derivative of our function, which we actually found up here, if I take the derivative of it, set it equal to 0, I'm going to have at least one solution to this equation, derivative equals 0, and that solution is going to be somewhere within the interval from x equals 0 to x equals 3. I'm guaranteed that from Rolle's theorem because I've met all 3 of these conditions here. Okay. So now what you'll see is the work that I do to do that. So of course, we know that f prime of c, just taking x and replacing it with c, ends up being this function here. We set it equal to 0. And by definition, we know that we could use the quadratic formula for that. And so we do that, plug everything in, and you see that we get these 2 solutions here, where we have 1 plus square root of 19 over 3 and 1 minus square root of 19 over 3. Now, if we notice here, 1 minus square root of 19 over 3 is not going to be within the interval from 0 to 3, mainly because we know that square root of 19 is bigger than 1. It would be, I'm guessing, somewhere in between like a little more than 4, so I'll just say like 4.2. So 1 minus 4.2 is going to be minus 3.2 divided by 3. That's going to be a negative number. Okay, so because of that, that's not going to be within the interval. But of course here, and let's say I say that this is 4.2. If I take 4.2, add 1 to it, and then divide that by 3, then I'm getting something like 1.7 something. And of course, I'm a little bit off with this number here. I actually typed it in the calculator and got a good approximation for it. But the number that I got when I did my approximation is like 1.73. So the big thing is that we see that that number, even though it's a little bit off, is in between 0 and 3. Okay. Thus, we know that at this particular value, which we approximate to be 1.786, if we were going to look at the graph of our function, we would either have a smooth peak or a smooth dip at this point C, which is going to be this 1.78. And of course, the corresponding y value for that, we have to plug this function back in, this number back into the original function to figure out what the corresponding y value is, okay? And for this particular problem, we're really not concerned about where that is. The only thing that we do know is that once we've identified that, hey, at this number approximately 1.786, we're going to have a point here that's actually going to have a horizontal tangent line there. And you can, of course, the function could look like this or this at that particular x value C. Rolle's theorem will not let you know if it is going to be a local max or a local min. That's really not the role of Rolle's theorem. It's just to say, hey, it's another thing to kind of let you know you have the potential of that. Okay. All right, so let's look at our second example here. Okay. So if we look here, we have this function, which is 1 minus the cube root of x squared, which of course we could express as 1 minus x raised to the 2/3. So what we want to do here is show that f of minus 1 is equal to f of 1. Put another way, we want to show that condition 3 of Rolle's theorem is being met, but that there is no number c that's going to be within the open interval from -1 to 1, such that f prime of c is equal to 0. So basically what we are trying to do here is show that condition 3 of Rolle's theorem is met, but we're not necessarily going to meet the other two conditions. And in particular, what's being stated here comes from condition number 2. Okay. Remember, condition number 1 was that our function is continuous over a closed interval. And if we look at what this function actually looks like here, and I'll try to draw a quick sketch of it. In general, this function would look something like this. Do it in a different color here. So we would have this point here, and the graph will kind of go like this, okay? And of course, right at the point 0, 1 here, what you have is a cusp in your graph, okay? I know because I had drawn a point there, it doesn't look like that, but it kind of has this shape like this. So there's a cusp there. And since it's a cusp there, we know that we can't take the derivative of a function at a cusp, okay? So what we're doing is just algebraically showing that. So here we show, again, if we take our function 1 minus cube root of x squared, that f of minus 1 and f of 1 are equal to each other. Easy to do, okay? And so we see here that basically what this is telling us is that at f of 1, or -1, and at f of 1, we have x-intercepts here. So function's kind of looking like this up to that point. However, if we take the derivative of our function, and you see that I've sort of looked at this in its fractional exponent form to be able to take the derivative of it easily. If I take the derivative of it, I get this function here. And of course, if I plug in 0, and of course 0 is a number that's in between -1 and 1. If I plug that into my derivative, I see that my derivative does not exist, okay? I put undefined here, but probably a better way to say it, the derivative does not exist, okay? So, so here we see that essentially, that because just because we had f of -1 and f of 1 being equal, that didn't guarantee us that we were going to be able to find any x value c here within this open interval from -1 to 1 such that we had a horizontal tangent line at that particular point, okay? And again, what you see here is that we have a cusp, but algebraically, when we work it out, what that looks like is you have some number divided by 0 for your derivative whenever you try to plug it in at the place where you think you may have, a horizontal tangent line, okay? All right, so why does this not contradict Rolle's theorem, okay? Well, again, all three conditions were not met. We met condition number 3, but we didn't meet condition number 2, okay? And of course, condition number 2 was f was not differentiable for every x value in between x equals -1 and x equals 1, okay? Because it was not differentiable at x equals 0. All right, let's move on to the next example. All right, so for this last example, we're actually going to work this out together here. And what we want to do is to verify that our function satisfies the conditions of the mean value theorem first. And then after we verify that it meets those conditions, then we want to find all possible numbers, C, meaning all possible x values that are within this interval here, that will satisfy the conclusion of the mean value theorem, okay? So I'll start with the conclusion first. So the conclusion of the mean value theorem says that we will be able to find a derivative of some function at some value C, which we know this means slope of the tangent line at some value x equals C of our function. And that will be equal to the slope of the secant line of our function going from x equals a to x equals b. So the slope of the secant line of our function from x equals a to x equals b will be equal to the slope of the tangent line of our same function here, but it's this slope of the tangent line is going to be going through a particular point, a point C, f of C, okay? And that value C is going to be strictly in between 1 and 4 in this case. So this is our conclusion, okay? What we need to do is to identify what are the conditions that allow us to be able to make this assumption so that we can find these values C that actually satisfy this equation here. So going back to the formal version of what the mean value theorem tells us, we know that it has to satisfy these two conditions, meaning is our function continuous on a closed interval, and is our function differentiable over the corresponding open interval from x equals a to x equals b. So we need to verify both of these. And we're going to do that first and then find out what that what the actual values of C would be that satisfies the result equation. All right, so first things first, let's take condition 1, which is f continuous on this particular interval here, okay? So if we look here, we notice that what we have here is a rational function. So here, f of x is a rational function. Now, why is that important? Well, one of the things that we know about rational functions are continuous everywhere in their domain, okay? So that means f is continuous. And this symbol here means for all values of x that belong to its domain. And I'm just going to call d sub f the domain of f. Okay. So in order for us to find out if this function is continuous for all values from 1 to 4, I need to know what the domain of this function is and make sure that if I have any discontinuities in this particular function, or if I have vertical tangent lines or or anything like that that would kind of, well, not say necessarily vertical tangent lines, but if I had any discontinuities, let's just keep it that way. What I meant was vertical asymptotes. So if I have any kind of discontinuities, I need to make sure that it does not happen at any value in between 1 and 4. Okay. Well, the domain of this particular function here is going to be all real numbers except for -2. Okay. So I'm just going to write it like that. Okay. And so here we see that, and that's -2, by the way. So since -2 is not in the domain of f, because again, we see here, -2 is not in the domain of f, then that implies that f is continuous. Oh, sorry. No. I'm supposed to say that since -2 is not in the domain of, -2 is not a member of this particular closed interval here. So pen's drifting on me. Right. So we see that the only value that's not in the domain of f is -2. And since -2 doesn't belong to this closed interval from 1 to 4, then that means our function f is going to be continuous on this particular interval. Okay. So pretty simple to show. We also need to show, is f going to be differentiable on the corresponding open interval? So is f differentiable on this corresponding open interval? Okay. Now, the simple way to show that is we need to find out what the derivative of f is. And then after we do that, show that the domain of the derivative is not going to include any values here that we actually need for this open interval from 1 to 4. Okay. So essentially find the derivative of this, find the domain of it, and show that the values that may not be in the domain are not values that are a part of this interval here. Kind of like what we did up here. So let's go ahead and find out what the derivative of our function here is. Using the quotient rule, we will have low function times derivative of the high function. And of course, derivative of x is 1. Minus high function times derivative of low function. So derivative of x is 1. Derivative of 2 is 0. And all that over bottom function squared. Of course, if we work all that out, it's just going to be x plus 2 minus x all over x plus 2 squared. And we see here that the x's here are going to cancel to 0. And what we're left with is 2 divided by x plus 2 quantity squared. And this implies that the derivative of, the domain of the derivative is also going to be all real numbers except for -2. And again, we know that because if I plug in a -2 in the denominator here, that will be the only number that will make my denominator go to 0. And thus, we would have an undefined term there. Now, again, since -2 is not a member of this open interval here, this implies that f is going to be differentiable on this open interval of x values from 1 to 4. Okay. So we see that our rational function that we're given over this closed interval is actually going to satisfy both conditions for the mean value theorem. And what this essentially means for us is that now I know that there's going to be at least one value c that will satisfy this equation. Okay. Now, just for clarity here, let's say instead, if I had this going from -4 to 4, okay? Let's say if I had this going from -4 to 4, and I tried to do the same thing here. Since the value of -2 is within this interval from -4 to 4, then this function under this closed interval here would not meet the conditions, would not meet condition 1, because I would basically have a vertical asymptote at x equals -2 that would be inside of this interval here, okay? And of course, if I take the derivative of this over the same closed interval, then you see that the domain of the derivative is the same as the domain of the original function. So again, we have that problem, okay? So that's why it's important to know what type of function you're dealing with, as well as what interval of x values you're dealing with as well. So now that we've verified this, we can now actually go and show that we're going to have at least one value c that's going to satisfy the conditions given to us, okay? So I'm going to say, therefore, f prime of c is equal to f of b minus f of a over b minus a, where c is going to be somewhere in between 1 to 4 is guaranteed. So maybe I should say here guaranteed solution. Yep, so let's do it like that. So we have a guaranteed solution to this. Okay. So to do this, of course, we already know what the derivative of our function f is because we found it up here. It's just 2 divided by x plus 2 quantity squared. So here I'm just going to say this is going to be 2 divided by c plus 2 quantity squared, replacing the x with c. Of course, if you remember here, this is our a. A is 1, b is 4. So we're going to have f of 4 minus f of 1 divided by 4 minus 1. Okay. And here, f of 4, remember that our function f of x is just going to be x over x plus 2. So this would just be 4 divided by 4 plus 2, which is 4 divided by 6, which is 2/3. Okay. And f of 1 is just going to be 1 divided by 1 plus 2, which is 1/3. So of course here we have this 2 divided by c plus 2 quantity squared. F of 4 is going to be 2/3. F of 1 is 1/3. And 4 minus 1 is 3. And so this will be just 1/3 over 3, which is 1/9. Okay. And so of course this means that 2 divided by c plus 2 quantity squared is just 1/9. And from here we just need to solve this equation for c. So we can do some cross multiplication here, quick and dirty way. So if we do that, then we'll have 18 is equal to C plus 2 quantity squared. And if we take the principal root of both sides, this will be plus or minus square root of 18. Let's try to make that look a little better here. Plus or minus 18 is equal to C plus 2. We can rewrite square root of 18 is just square root of 9 times square root of 2. And of course, from here, we know that square root of 9 is just 3. And if we subtract 2 from both sides here, then we would have minus 2 plus or minus 3 times square root of 2 will be equal to C. And so we know that one of these two solutions has to be it. And so we want to note that this solution minus negative 2 minus 2 times square root of 3 is not going to be within the interval from 1 to 4. And we know that because it's negative. Okay. So this means that C is equal to negative 2 plus 3 times square root of 2 is the only solution. Okay. All right, and so the beginning of this problem again was to verify that our function under the closed interval here met the conditions for the mean value theorem. And the mean value theorem says that we're guaranteed a solution to this particular equation, meaning we're guaranteed at least one value of C here that would make both sides of this equation equal to each other if we met these two conditions. We saw, using what we know from continuity in a first year calculus course and differentiability in a first year calculus course, that this function for this particular closed interval did meet both conditions. And then, of course, from that point, we just substituted in everything that we needed to be able to solve for what C actually was. And we got rid of the value that did not go with the interval that we were looking for. And of course, the interval was was a closed interval from 1 to 4. But in terms of the differentiability here, we have to actually pick something that's strictly in between. So that's why we're really concentrating on the values that are strictly in between 1 to 4 to say, hey, this particular value is going to be a solution for it. All right, so I have 2 more examples that I want to go through. These last 2 examples will be more like proofs versus, hey, we just have something, we verify that our function meets this condition, and then we do some algebra to figure out the answer. So, and I've thrown these in here so that you can actually see how we use the mean value theorem in a way that's less computational, and we're actually doing a little bit more thinking at a higher level here. Okay. Now, just with the, just like how we use the intermediate value theorem to be able to prove the existence of solutions for an equation, and we do that by basically re-engineering the equation to say, we're rewriting it so that we can basically solve for the x-intercepts, and we use the continuity properties to verify that, hey, we have, because this function is continuous in between this value and this value, we know it had to cross the x-axis somewhere. So that's one way that we use the intermediate value theorem to be able to prove the existence of solutions, even though we may not know exactly what they are. I'm bringing that up because we can also use the mean value theorem to do the exact same thing. Okay, but in using the mean value theorem to do it, we actually employ the intermediate value theorem to help us get started here. Okay, And so what I'm doing here in the first part of this quote unquote proof is essentially using a version of the intermediate value theorem to establish a baseline of how many solutions I could possibly have. Okay. So I wanted to go ahead and put that out there first before I went through this example here. Okay. So we want to show that this particular equation here has exactly one real root, meaning it only has one value of x I can plug in here and here that would make the left and right sides of this equation equal to each other. Okay. Or put another way, for this particular, if we looked at 2x minus 1 minus sine x as a function, it's only going to have one x-intercept. Okay. So that's a way that we can look at it. So my hint here is we want to find an interval from a to b such that f of a and f of b are of opposite sign, given that this function is allowed to be 2x minus 1 minus sine x. Okay. Now, this first sentence here is essentially one of the ways that we actually use the intermediate value theorem. So that's why that sentence is stated there. So we know that if I can show you, hey, this function is continuous over a closed interval, I can guarantee you that all the values in between this a and this b would actually have a corresponding y value to go with it, where those y values should be in between this value and that value. Okay, so that's what we're going to try to do first. If we can do that, it makes it easy for us to be able to use the mean value theorem or Rolle's theorem or whatever it is that we're going to try to do to establish the rest of what we're going to try to do here. Okay. All right. So, and I'm telling you here that I'm going to use a method of contradiction to show that we only have one real root. Okay. So let's just get started, and then I'll kind of coach you through the rest of it. So here I select this particular interval from 0 to pi over 2, okay? And I let my function here be 2x minus 1 minus sine x. Now you may ask, why did I choose a value, why did I choose an interval from 0 to pi over 2, okay? In using the intermediate value theorem, one of the things I want to be able to do is to have f of a and f of b have opposite sign. I also want to be able to choose a value or values of x that are going to be relatively easy for me to evaluate this function by. Okay. Now, I noticed that the easiest value of all of them to evaluate this function by is 0. And if I evaluate it at 0, do you see how I get a negative number? Okay. Now, of course, I could evaluate sine at, pi over 4 if I wanted to. And I know that would be square root of 2 over 2 or 1 over square root of 2, depending upon how you interpret it. But I know that sine of pi over 2 is just 1. Much easier to deal with. Okay. So that's why I chose pi over 2. And notice that when I do that, I got this expression of pi, which is approximately equal to 3.14 minus 2. And I know that's going to be a positive number. So I know that by letting my a be 0 and my b allowing it to be pi over 2, I notice I have the sign change that I'm looking for. Okay. And now I also know that 2x minus 1 on its own is a function that is continuous for all real numbers because it's a line. I also have sine of x, which is also a continuous function for all real numbers. And one of the things that we know about functions that are continuous, if I take two functions that are continuous for all real numbers and I take the difference of those two functions, I'm still going to get a new function that's going to be continuous for all real numbers. Okay. So knowing all that, I have the sign change that I want here, and I know that my function is going to be continuous on this closed interval here, since both of these functions are continuous for all real numbers. Okay. And of course, that means the difference of it would also be continuous for all real numbers, which means it'll also be continuous on this shorter closed interval. Okay. Now, this last sentence here is just me kind of collecting everything that I know. And you notice here how I let n equal 0. And that's because of the intermediate value theorem, that portion of the theorem that says that we have a guaranteed solution for f of c is equal to n, where, of course, we're considering this closed interval here. This is the conclusion of the intermediate value theorem if our function is going to be continuous over closed interval. So I'll let that n equal 0 there because we're essentially trying to figure out when does our function equal 0, okay? Or when are we going to have an x-intercept? So if we look at all that, then by the intermediate value theorem, and that's really what I was setting all this up for, and by the intermediate value theorem, I know that there is at least one solution, f of c is equal to n, and of course, in place of this n, I could just put 0 there, okay? So what I've actually done here to say that by the intermediate value theorem, this particular function, well, we have at least one solution to this particular equation here, which is there's some value in between 0 and pi over 2, such that when I plug it in, its corresponding y value is going to be 0. Intermediate value theorem guarantees that, okay? Now, when I say we have at least one solution, that means I could have one solution, two solution, three solution, four solution, infinite many solutions, okay? But all the intermediate value theorem says is that, hey, I guarantee at least one, okay? Doesn't tell you how many, it just says at least one, okay? So now what we want to do to try to up the ante a bit is we want to assume that, all right, well, let's assume that we don't have just at least one. Let's assume that we have at least two, or let's say we have two solutions, okay? What conditions are we going to have to meet to be able to make that assumption, okay? So if I want to say that I have two values of c that I can plug into this function that will ultimately end up equaling 0, then, and I know that both of these values of c have to be in between these two numbers here, then what's going to have to happen here is a situation kind of like what I've drawn here in figure star, okay? Now, notice that I'm giving you one variation of a theme of what this could be. I could also have a situation like this as well, okay? So without loss of generality here, I'm just using the case where the function increases and then decreases, okay? But notice we can do the same thing if I draw when I'm talking about the other one. And again, we don't care about what the entire function looks like. I just care about what the function should roughly act like in between x equals 0 and x equals pi over 2. So if I say that I have two values, c1 and c2, to where if I plug it into my function, I'm going to get 0 for an output, then that means that corresponding y values for these x values here has to be 0. Hence, I got to have x-intercepts here and here, okay? Now, because of that, notice that if I consider the closed interval here, or the closed interval here, but in particular the closed interval from C1 to C2, notice that these two x values have the same corresponding y values. Don't necessarily have that here, so I'm not going to use these values here to try to get to my point here, okay? So if we consider this closed interval here, in order for this condition to happen, I essentially know that I am going to have a horizontal tangent line at some point strictly in between C1 and C2, okay? And so whenever these x values here have corresponding y values that are the same, and I know that my function is continuous over a closed interval here, and it is differentiable over this corresponding open interval from C1 to C2, So if you remember here for Rolle's theorem, that's exactly what we said. Function has to be continuous on a closed interval from A to B, has to be differentiable over a corresponding open interval, and f of A and f of B have to be the same. And of course, in this case, this is going to be 0 here, and this is C1 and that's C2. And we're considering this is just C1, C2 now. So we've kind of changed it up a bit to kind of, push in our closed interval a bit. All right, so if we are just considering this closed interval from C1 to C2, then Rolle's theorem guarantees that we are going to have at least one value that's in between C1 and C2 where we should have a point, and the tangent line that goes through that point should be 0. Another way to say that, f prime of C is equal to 0, okay? So what we do is we take the derivative of our function. So remember, our function here is 2x minus 1 minus sine of x. So I'm going to let x equal c, and I'm going to take the derivative of it. Of course, if I take the derivative of 2x, that's just 2. Take the derivative of the constant minus 1, that's just 0. And I take the derivative of sine, well, minus sine, that's going to be minus cosine. So I have the situation here, set it equal to 0. And when I try to solve this, I see that I have a problem. And I know I have a problem because I know that cosine, my basic cosine function, only has a range in between -1 to 1. And I'm asking it what x value, c here, has a corresponding y value of 2. And I know that's impossible. So because of that, I have a contradiction. So what this tells me is that my assumption that I made here, I'm going to circle it. This assumption that I made here of my function having 2 solutions here, that is not valid. So since that's not valid, the only thing that's left here is that I have at least one solution to this equation, and the value is going to be in between these two x values here. So I know I can't have 2 solutions, but I know I have at least one solution. What that tells me is that by default, I can only have one solution. Hence, I only have one real root to this particular equation here. Or put another way, my function is only going to have one x-intercept, okay, for any value of x that I'm choosing here, okay. All right, so this is our last example. And again, this will be another proof-like example here. And again, I'm doing this to show you how we can actually use the mean value theorem to be able to prove the existence of solutions without us necessarily knowing what those solutions actually are. And so you may be wondering, why do we even want to do that? Well, in mathematics, one of the things that we would like to know is if there is a solution for some type of equation, or is there something that we're trying to look for, we want to know, are the conditions in place for that thing that we're looking for to be there before we go spend all the the time and or money, whatever to actually go find that, okay? Because it may take a lot of effort to be able to find out what it is that we're looking for. We need to know, is it worth it in the first place, okay? I guess an analogy I could use is if we have an astronomer who's trying to figure out, hey, if I'm looking through my telescope and I need to figure out, is this speck of light that I'm seeing here that I'm thinking is a planet, how do I know if that planet's going to be like Earth? Well, they may have found out that from other planets they assume to be like Earth, the light may reflect off, off that planet in a certain way, or there's some other property that they know of that says, hey, well, we see that sort of thing. We know that planets like Earth. Planets that are not like Earth, they don't want to deal with. So if they look at these planets through their telescope and they say, well, hey, we see that the light reflects off of the planet this way, or some other property. If they see that, then they know, hey, this has a chance for us to find what it is that we're looking for. If they don't see that property or properties happen that way, they're like, nope, not going to consider it, not even going to waste our time. Okay. So just like that analogy, in mathematics, we want to be able to know, hey, if I go searching for something that I know that may be hard to find, I at least want to know I'm going to find something when I get there. Okay. All right. So we want to show in this problem that this quartic equation here, or this quartic function equaling 0, has at most 2 real roots. Okay. So we have some polynomial of degree 4, and we have a family of them because we have this constant c that's here. So we're considering a whole family of quartic type functions. Okay. And since we're considering a whole family, we're saying no matter how the function looks, if it is a quartic function, the most that is going to cross the x-axis is 2 times. Okay. A quartic function of this family, the most that is going to cross the x-axis is 2 times. That's another way to translate what it is that we are trying to prove here. Okay. So the first thing that we do is we say let f of x be this polynomial expression here. So we're going to let it be a function, and we say, hey, c is going to be a constant. Since we want to show here that we have at most 2 real roots, the first thing that we want to do to start at a foundational level is to say, well, let's assume that we have at least 2 roots. Okay. If I can meet the conditions of at least 2 roots and satisfy that, then I can up the ante a bit and say, well, what if I have 3 real roots? Okay. And then I need to show that if I have at most 2, that my assumption of 3, something's going to break down. Okay. So here, let's assume that our function has at least 2 real roots, c1 and c2. Okay. Then we know that there's going to exist at least one solution to the derivative of this particular function here, evaluated at some value d, and the value d is going to be in between these 2 values here. Essentially, what we are doing is quoting Rolle's theorem again. Okay. So what's not being said here is that since we want to find out where we have x-intercepts, we're assuming that f of c1 and f of c2 are both going to be 0 here. Okay. Pen has a little delay here. So we're not actually explicitly stating that, but we're assuming here that c1 and c2 are going to be 0. So that meets the third condition of Rolle's theorem. And since this function is a polynomial of degree 4, we know that it's going to be continuous for all real numbers. So it'll be continuous on any closed interval that we consider. It's also going to be, the derivative of it is also going to be continuous for all real numbers. So it's also going to be differentiable for any open interval of x values that we choose. So we have all that. We know that, again, this last sentence here that I'm talking about, I'm essentially quoting Rolle's theorem. Okay. So if I assume that this function here has 2 x-intercepts to this equation here, then I'm saying that Rolle's theorem would have to be true. Okay. So I go and take the derivative of this function here. And of course, the derivative of x to the 4th is going to be 4x cubed. And notice I replace x with d, so it's just going to be 4d cubed. The derivative of 4x is just going to be 4. And notice that once I do all my math or whatnot, let's see, this should be a -1, by the way. That I know that this particular factor, set that equal to 0, is going to give me a -1. If I set this quadratic factor equal to 0, I'm going to get this complex number. Okay. Now, I'm asking what values here are going to give me two real roots. And hence, that's why I said x-intercepts, because an x-intercept conceptually is a point on an xy plane to where I give you the y value, I give you the x value, the y value 0, okay? And of course, we're talking about only real numbers here, not complex. So since I got these two complex numbers here, I can't consider that in my answer. I only got one real number answer here, but that's fine because Rolle's theorem guaranteed at least one solution. I have the at least solution here, okay? So according to my assumptions, I stated Rolle's theorem had to be true, and it was, okay? And so that means that my f prime of d here has at least one solution, and of course it's namely when d is equal to -1, okay? So what I've established at this point is that we have at least two real roots. Now, I have not established that I have at most two real roots. I've just established that I have at least two real roots, okay? And so I'm going to write that in here. Therefore, we have at least two real roots, okay? So now what we're going to do is up the ante some. So now we're going to assume that f of x has exactly three real roots, okay? So instead of assuming that we have two numbers that we can plug into our function that will give us an x-intercept, we're going to have three. And again, without loss of generality here, my quartic function may look like this, okay? I could draw it to where the function's kind of going like this and then goes down like that and then does like that again. I could do it like that if I wanted to. But regardless of what I do, and part of the reason why I didn't do it that way for this particular example here is because the family of functions that I have to deal with let me know that the end behavior of the quadratic function has to be like this, okay? So I could have done it to where I've drawn the function to where it bounces off here and it goes through like this and comes back up like that. I could have done that, but it doesn't matter how we do it. I know that this end behavior has to be like this, and that's mainly because the leading term here is positive. So I know for a quartic function, which is going to be the degree is even and leading term is positive, I know my end behavior has to be like this for that function. And of course that comes from pre-calc, okay? So in noting that, and I'm going to erase the rest of this here. So in noting that, that's why the picture I've drawn here will work for our situation, okay? So if I know that my function has three x-intercepts in between, it's going to have, just basically going to have three x-intercepts here, then this is what it's going to look like. And again, I'm considering this over all real numbers here, okay? So here's my first one, here's my second one, here's my third, okay? If that's going to be true, then notice that per my situation, I have two instances to where I have either a smooth peak or a smooth dip in my graph, and thus I'm going to have a horizontal tangent line at some point where one of those tangent lines is going to be located at a point D that's in between C1 and C2. The other one I'm naming W, and that's going to be in between C2 and C3, okay? So somewhere in between C1 and C3, I'm going to have two of these values here that are going to produce basically places where I have a critical value, okay? Or places where I have potential peak or dip in my graph. And I know that because I'll have a horizontal tangent line there, which means the derivative of the function at d and the derivative of the function at w are both going to equal 0. Okay, so that has to be true if I have exactly 3 roots or 3 solutions to this equation. Okay, now if we have exactly 3 real roots, then of course, like I said before, then at least 2 real numbers d and w are got to be in between c1 and c3, where we know that this is true. Okay, and again, this needs to be a -1 here. However, when we solve for f prime of d, or just in general f prime of x, and I'll go back up here for that. Okay, whenever we took our function here and we said, hey, I'm going to take the derivative of it, set it equal to 0, let me know what all the real number values that I can come up with that satisfy that. Notice that we only found 1. We still have the same function that we're dealing with. Okay, and no matter how many times I take the first derivative of it, I'm only going to have 1 value here that satisfies this. If I have 3 real roots, notice that I'm forced to have 2 values, but I know that that's impossible. Okay, and so that's what I'm trying to communicate here. But when we solve for f prime of d, and you can throw in here f prime of w equals 0, we see that f prime of d only gave us a solution of d equals -1. Okay, now f prime of w, when we set that equal to 0, that is also just going to be -1. Okay, so regardless of how you do it, you're still going to end up with d and w being the same number. Okay, and notice up here in our graph, d and w have to be 2 distinct numbers in order for this to be true, but it can't be because they're both the same. So hence I can't have this situation here. I can only have the situation here where, let's say my graph either looks like this or it looks like this. Okay, and that's essentially what Rolle's theorem was telling us whenever we established that we had at least 2 real roots. So because of that, we know that we have a contradiction. Okay, and looks like I spelled that wrong, but that's okay. Not a contraction, this is a contradiction. So anyway, so we know that we can't have these 2 numbers here because of that. Okay, we can't have these 2 values here that are going to be distinct to give us, this situation for 3 real roots. So we know that we can only have 2 real roots because of that. Okay, so after the contradiction, we just essentially say, hey, everything that we thought from this particular point on is all for nil. Okay, in other words, not going to work. And so what we have to do is go back to, actually, it was at this point, sorry. So everything from this point onward can't really assume. And so the last thing that we established that we had at least 2 real roots. And of course, since we can't have at least 3, we know that we have to have exactly 2. And that's how we end it. Okay, so this concludes the video on mean value theorem, its interpretation, some examples of how we use the mean value theorem, both from a computational standpoint as well as a proof standpoint. I hope this helps. Take care.